So when Matthew and Ashish asked me what I wanted to talk about associated with something had to be a little bit associated with LSST, I thought what I'd talk about might be how we are looking for slow-moving asteroids in the outer solar system by stacking up images taken over multiple days or multiple years of observing. And this is it's a really interesting problem. It's an interesting problem from the context of LSST that if you get the cadence right, if you get how often you come back to the same point on the sky and how much of the sky you survey as a function of time, if you do that correctly, then in the first year of LSST observations, you could detect 10 times more Kuiper Belt or trans-Neptunian objects than LSST is expected to detect over the period of 10 years. That's going from 40,000 TNOs up to about 500,000 TNOs, just with a year's worth of LSST data. And that could really transform our understanding of the outer solar system and even begin to probe the inner parts of the Oort cloud. It's also really interesting from the software engineering perspective, where we have to use GPUs to accelerate the search for these slow-moving objects that are below the detection limit of any individual image. And also you have to move these images in and out of the CPU and the GPU memory. And it's interesting from the perspective of the statistics because it's almost like real bogus on steroids because you're doing real bogus in actually stacks of images or temporal images. And you also end up with some interesting statistical questions that we've done with Stefan Portillo, which is how do you determine when to give up? How, when you're searching for a slow-moving asteroid, would you say that there's just no more evidence and you can stop the search? And that can actually give you factors of 2 or more speed up. So thinking about that on the flight down, I decided I wasn't going to talk about any of that stuff. I'm not going to talk about machine learning. I'm not going to be talking about deep networks or applied to images. I thought what I'd do instead is to talk about something that we've been working on for the last couple of years. And it's more of a statistical methodology. And the question is really, if you want to look at things, how do you do it in a way that makes everything look as good as possible? And one way of thinking about that is in the context of coming from the UK and now living in the US, how do I create a set of rose-tinted glasses that make everything look as happy as possible given the current situation that we're in terms of our political climate? So more accurately, you might actually say, if I've got a large imaging survey and I want to observe through that imaging survey in different filters, how should I actually choose the filters that I observe through? If I'm investing $500 million to $1 billion as an instrument, shouldn't I invest a lot of time in choosing the wavelength dependence, the response function of the filters themselves? And so this is some work that was done by Bryce Kalmbach and Jake van der Plas and myself. Bryce Kalmbach is a graduate student or just graduated from the physics program at the University of Washington, and he has now moved into a postdoc position working on LSST commissioning. Jake, as many of you know, was the head of research at the eScience Institute at the University of Washington, and about 6 to 9 months ago moved to take a permanent job at Google. Now, with any science case, I think you should always ask the question, why should I really care about studying this sort of problem? And the question that we want to address is, if you look at a telescope such as the LSST, and this is an image of the LSST as was taken about 3 weeks ago. So you can see all of the infrastructure for the dome. If you look at it today, you'll see that the paneling on the actual outside of the dome is beginning to be put in place. We expect to be able to close the dome before the end of the northern summer, the southern winter, and then have the telescope mount assembly moving out to the telescope by the end of the year, and the first operations of the first commissioning camera to start within about 2 years from now. You can see this is a contractually obligated picture of the LSST, that all LSST pictures must have no cloud, because that is the expectation for the survey. And you can see that this is just a view of the LSST, and on the left-hand side you can see the auxiliary telescope, which will be the calibration telescope for the LSST as a whole. So if you're looking at a survey like the LSST, or if you're looking at a space-based survey such as Euclid or WFIRST, then there's lots of constraints on the response function of the filters you should actually be working with. We have a finite amount of observing time. We have to distribute that observing time over a range of different filters. For the LSST, we have a filter exchange mechanism that can run for a few 100,000 before it's expected to fail. And so you want to minimize the number of filter exchanges. And you want to do that anyway, because it takes between 1.5 and 2 minutes to actually do the filter exchange. And so that adds a significant amount of overhead into the cadence of the observations. There are wavelength-dependent issues in terms of sensitivity. We have the sensor itself and its response function, a function of wavelength. We have the atmosphere cutting off in the ultraviolet. And we even have the fact that the beam of the LSST, the angle that the beam passes through the filter when you're working with interference filters, actually changes the response function of it shifts by about 1 to 2% the actual wavelength response function of the filter. And finally, we have all of these competing science objectives. If you were looking for trans-Neptunian objects in the sky, you wouldn't really want to do a U, G, R, I, Z, and Y passband survey. You probably want to either just work in R and I, or just have a broad, wide filter to go as deep as possible. Whereas if you're looking at stellar colors, then you want to have this multispectral set of observations. So there are many competing aspects associated with with how we should actually observe using these telescopes. And if we look at what's been done to date, our choice of filters has been somewhat ad hoc. Right? So if we look back to the original Johnson-Cousins filters, we can see these, the UG or the UBVRI filters from Johnson and from Cousins, and you can see that the filters actually overlap with one another. And this is all driven by the properties of the glass. They're glass-based filters, and so the tail-off of the sensitivity towards the red end is all determined by the properties of the glass. When we move to more modern surveys like those with the Sloan Digital Sky Survey, we have sharper edges to the filter because we're beginning to use interference filters. You can also see that what we do is when we have a spectral range that's defined by about 3,000 angstroms for the transparency of the atmosphere, out to about 1.1 microns when the silicon becomes transparent and the photons just pass through the silicon, the natural thing to do is if you're given 5 filters, you distribute those 5 filters across the full wavelength range. You have sharp edges and you have gaps for the SDSS, and these gaps correspond to wavelength regions such as 5577 for the strong sky emission lines. But gaps in the filters introduce significant problems with photometric redshifts estimators, as Kai was talking about. And we've seen those effects. So if we look today at projects like LSST, we have a distributed set of filters. We have sharp edges, but we get rid of the gaps. But I was involved in both the development of the filter complement for SDSS and the shapes and filter complement for the LSST. And the way we approached this problem was from a fairly ad hoc perspective, right? We had a set of basic science questions, and we said we want to distribute these filters. We probably want them to not overlap, but we don't want them to have gaps. And we have a couple of science cases that we're going to make sure that they're not optimal for, but they're not, they don't degrade a lot of the science. But today, and if you actually then go into kind of intermediate band filters, whether it's the Geneva filters or the Stromgren filters, then all bets are off and you can choose whatever filter set you want. But what's really interesting is today, with technologies such as the interference filters, we can design our own custom filters. So we can design very narrowband filters like you might get from the JPAS survey. We can also design comb filters, which will be a set of filters with narrow bands, but a whole set of these narrow bands across in one individual filter. So you're actually producing some sort of comb. And now you can start asking the questions, what's the optimal combination of these sorts of comb-like filters? So that's what got us thinking about the question of how should I actually design a survey And the reason that really drove this was thinking about projects like Astro 2020. So after 10 years of the LSST survey, what would you do next in terms of observing with a telescope that's got an 8.4 meter primary and a CCD or a camera on the back end with 3.2 gigapixels? So I'm going to give about 3 slides on entropy, conditional entropy, information gain, just to give the background, even though I think a large number of the people in the audience know all about entropy. So the basic idea is, how do we quantify uncertainty in some properties? So the redshifts of the galaxies, or the type of a galaxy. And we choose entropy, and entropy is just defined as the probability times the log of the probability. And the simplest example of this would be if you imagine that I was just flipping coins, and I just took an unbiased coin, so it's 50% heads and tails. So I can calculate the entropy associated with that. It's 0.5 times log base 2 of 0.5, multiplied by 2 because I've got 2 possible states in terms of the heads and the tails. And that gives me an entropy of 1 bit. Okay? And then the second thing I could do, well, what happens if I bias one of the coins so that it's 90% of the time it falls on heads? And I can calculate, so naturally what I would want to do if I was going to predict what the property of that coin was going to be is I'd always predict heads, and I'd be correct 90% of the time. So if I calculate the entropy associated with that, it's 0.46 bits. If I calculate a fully biased coin that always produces heads, then the entropy is 0. So as I decrease the entropy, then I'm decreasing the uncertainty on my predictions. So that's entropy. Conditional entropy takes it one step further, which is saying, how does the entropy change as my knowledge of the system changes? So if I make a measurement, how does that change the entropy? And a simple example of that would be if you looked in this room, we're all flying on planes over the next few days, 30% of us will get sick from flying on those planes. However, if I look at that population as a whole and I break it down by age, and we'll just split it 52 years. I don't know why I picked that number. It just seemed appropriate to me. So if we split this into 2 halves, and it turns out that it was 20% chance of being sick if you're under 52 and 80% chance of being sick if you're over 52, then if I take a measurement which is to ask your age, then I get an improvement in my ability to make these predictions. And so in this case, what we are doing is we're looking at the conditional entropy. So the conditional entropy, which is the probability of the illness given the age. Right? So that just says that if I make a measurement, how does it improve my understanding of the system as a whole? And then if we put this all together, we can look at the information gain, which is just the change from the original entropy minus the conditional entropy given that I've made a measurement. So it's essentially measuring the effectiveness of my measurement. And in the cases I'm going to talk about here, the Y value that I'm going to be thinking about is going to be the redshift of a galaxy, or the spectral type of a galaxy, or it could be the spectral type of a star. And it's just a way of quantifying the uncertainty associated with predicting the redshift type of a source given a particular measurement. And the measurements I'm going to make are colors of galaxies, as Kai introduced when he was talking about photometric redshifts. So I'm going to show you a couple of simple kind of toy model examples, and then I'm going to deploy it for the LSST as a whole and see what conclusions we can actually make. And these toy models, let's look at the first one, which is, imagine if I had 2 spectral energy distributions, two spectra, and I said I was going to give you 2 filters, and those 2 filters, I'm going to let you choose wherever you want to place those filters as a function of wavelength. And naively, well, not naively, just based on our understanding of spectral energy distributions and colors of galaxies, what you would probably say is, if I wanted to differentiate between these 2 spectral energy distributions, the red and the blue, I'd put one filter at the blue end and one at the red end. I might put one filter around the 4,000 angstrom break and one in the red end. And if I was to plot the colors of the galaxies, of these 2 galaxies, as a function of the position of one of these filters, you can see that when the filters overlap, there's no color, there's no information. As I separate those filters, then I get color information. If I calculate the information gain, so given a measurement of color for those two filters, how much information do I actually gain? Then if I just look at, this shows you the information gain as a function of the position of filter 1 and the position of filter 2. So let's just fix filter 1 at a wavelength of about, say, 4,500 angstroms. And then I'll vary filter 2 as a function of position. I'll see how the information gain changes. When they're both at the same wavelength, dark here corresponds to no information gain, bright corresponds to a lot of information gain. So when they're overlapping and there's no color information, then there is no information gain. As I move that filter away, so separate those filters so they're no longer lying on top of each other, we get a significant information gain. You'll see that it's a very sharp feature or sharp change in the information gain as a function of wavelength. And that's because these are essentially infinite signal-to-noise measurements. And so if you think about it, what's happening is if I've got infinite noise measurements, I'm essentially got almost like two delta functions sitting on top of each other. And so as they separate, those delta functions separate in the context of entropy, the entropy doesn't change depending on how far apart those two delta functions are. Right? You only get a significant gain when you change it from them being on top of each other and moving. And that makes sense from the context of the colors. If I have infinite signal-to-noise in the colors, then as long as I have some measurement of the color, I can separate out these two galaxies. Right. It changes a little bit when you add noise into the system, because when you add noise into the system, you can see the change as a function of separation of the filters is a much shallower slope. And the reason for that is now that there is, essentially I've got two Gaussians, where they're either sitting on top of each other, or as I separate those two Gaussians, and the Gaussians are defined by the photometric error associated with each of the sources, I have to separate them significantly before there's no overlap between those two Gaussians. Right? So this is the optimal or the best filter choice based on the entropy. You can see it places one filter at about 450 nanometers and the other about 850 nanometers, which makes complete sense intuitively if what we would do in terms of separating out these filters, or separating out these two spectral types. So essentially, Y here is the spectral type of the red and the blue spectrum. I can extend this out to include redshift. So now what I'm predicting is what is the information gain on the redshift distribution of a set of sources, given a particular set of filters. Right? So to do this, we put in a prior for the redshift distribution that's comparable to LSST, has a peak in the prior for the redshift distribution of 0.55. And then we say, tell me where to place those two filters. And the best choice for the filters is shown by this red dot here. And what we can see is the two filters based on the maximum information gain are at around, 580 nanometers and about 900 nanometers. And so if I take this spectral energy distribution that I had for one of those galaxies, and I shift it to the mean or the median redshift for this redshift distribution in my prior, so I shift it to a redshift of 0.55, you can see that the optimal position of the filters is to put one bluewood of the 4,000 angstrom break and one redwood of the 4,000 angstrom break. So again, it makes intuitive sense that you're placing these filters, the best place to put the filters is either side of the 4,000 angstrom break, where that 4,000 angstrom break is at the typical redshift for a galaxy. That gives you the most information gain for the system as a whole. And all we're really doing here is taking a set of filters, and if you look at each one of the different spectral energy distributions that I'm going to be working with next, you can see each SED has a Gaussian uncertainty, and that's given by the signal-to-noise of the observations. The colors of each one of these SEDs are correlated with the redshift. Okay? High redshift is yellow, low redshift is blue. And all we're really doing is defining the filters so that given one color in a particular set of filters, you want it to have a smaller dispersion in redshifts as possible. Now, this is not using any photometric redshift techniques, template fitting, deep learning, or anything. It's just looking at the statistical properties of the redshift distributions themselves. So you can see now here where I have high information gain, then each color that I'm looking at, each position on this, along this color axis, has a well-defined redshift associated with it. Where I have a system that has low information gain, then all of the different redshifts sit on top of one another for a particular color. Okay. So again, it's intuitively making sense. So now we're going to expand this out to LSST as a whole and thinking about the full distribution. So we're going to look at a population of galaxies going down to I of 25. I of 25 is known as the gold sample for LSST. That's the high signal-to-noise set of observations that after 10 years, I think has a signal-to-noise of about between 20 and 50, depending on which passband you're working in. And this is the sample that we expect to apply weak lensing tests or weak lensing measurements to for most of the weak lensing cosmology. And it amounts to about 4 billion sources by the end of 10 years of LSST. So we're using that as our nominal sample. The redshift distribution has a peak at around a redshift of about 0.9. And that's what we use for our prior that I was showing previously. We increase the number of templates. Instead of 10, we go to 2. We look at redshift bins from 0 to 2.5. We apply the appropriate signal to noise of these observations. And then we can start asking questions such as, if I had an extra year of observations associated with the LSST, so thinking about 2032 and the 2020, Astro 2020, what should we be doing at the end of LSST? What would be the optimal filter to observe if you were working in a broadband filter for LSST? And the example for this is if we use the entropy-based or the information gain approach and we say, I want you to design a filter for the LSST that maximizes the information gain, given that I already have this set of 6 filters from LSST, you can see that the optimal design for this would be to place a broad filter, so you're maximizing the signal to noise, so you're increasing the number of photons, with the filter centered around 700 nanometers, which corresponds to where the 4,000 angstrom break sits at a redshift about 1.9. Okay. And it also, if you were to artificially change that prior to make the typical galaxies sit at a redshift of, say, 0.5, then the optimal filter is now shifted into the ultraviolet, to the blue end. Okay? The second question you can ask is, what should our filters actually look like? So there's been a lot of interest on whether you should have narrowband filters, whether you should have triangular filters, whether they should be all top hat, whether they should overlap by 50% so you get redundancy in the actual colors. How should I actually design those filters? And so we can look at the information gain as a function of shape of the filter, and we express this as a ratio of the top of the filter to the bottom. So 0 corresponds to a triangular filter, 1 corresponds to a top hat filter. And you can see you get significant information gain up until the point where you have about an 80%, so like a 20% slope at the edges of the filter. Right? And this allows us to put this together and say, imagine if I was redesigning the LSST today, and I said, purely from an entropy information theoretic perspective, what would the design of filters actually be? And we can calculate that, and it ends up being about a 24-dimensional system that you have to optimize. So it's tractable. It's a little bit slow. It takes a couple of days to run this. There's a lot of software engineering that goes into this where we're using a lot of the properties of Gaussians and multiplications of Gaussians in order to sample this 24-dimensional space. But the design, this shows you the LSST filters themselves, and these are the optimal filters that you would observe or you would generate if you just used entropy or information gain, trying to optimize the redshift distributions. And so what you can see here is just, if we compare them to LSST, to first order, it's relatively close, right? We spread the filters out. They're approximately the same width. We don't have slopes. We do have overlaps between the filters, which are comparable to the overlaps in the LSST, but we have much more of a top hat shape. The only major difference between what we did for LSST and designing them this way was that we make the G-band filter much broader and continue into the U-band. And this is to increase the signal to noise because the sensitivity of the detectors in the U-band is significantly lower than it is in G, R, and I. Okay. So coming back to what Kai introduced with photometric redshifts, so everything I've done has nothing to do with photometric redshifts in terms of any of the techniques. So I'm just going to demonstrate the performance of these filters from a photometric redshift perspective. And I'll just skip over this fairly briefly, but as Kai was saying, that if you take a photometric redshift, what we're really doing is we have a filter, a spectral energy distribution that passes through these different filters. If we look at the color as a function of redshift, as we change the redshift, the color changes. And all that photometric redshift is really doing is to say, given a point in this color space, what is the redshift distribution of the sources at that point in color space? And that can be done with training sets, it can be done with neural networks, it can be done with template fitting. We do this with a color-based nearest neighbor matching technique that we introduced a couple of years ago. It uses the, I can't remember what it is. It uses a color matching technique that is, will come to me by the end of the talk. It predicts the colors from a training sample. We do this with simulations. We look at 4 metrics that are interesting: bias, standard deviation or scatter, and outlier fraction. Bias is any intrinsic changes between your predicted and the true redshift, and that's important because if you get systematic changes, then you introduce errors in your cosmology. Scatter is important for things like baryon acoustic oscillations to isolate shells in redshift, and outlier fraction contributes to the bias. So the only thing I would say is if you compare LSST plus an extra filter, there is no real improvement in the photometric redshifts. If you redesign all of the LSST filters, and one LSST filter costs about $500,000 to make, so it's worth investing time in choosing these filters, then you get some improvement in the outlier fraction at low redshift, which makes sense because you're investing more of your observations into the U-band and the G-band. And you trade that improvement in low redshift for a degradation at redshifts greater than 1.5. So just to kind of summarize, this doesn't have to just be applied to colors of galaxies and their redshift distributions. It can be applied to colors of stars. It can be applied to metallicity estimators. It's a generalized technique or framework for determining what the optimal filters are from an information gain or entropy perspective. What are the optimal filters to minimize the uncertainty on some property that you're interested in? Where we're interested in going is to increase the dimensions from 24 up to about 200. That will allow us to use these comb filters. We're particularly interested in the idea of having interleaved comb filters, particularly if you have the beam of the LSST. The angle of that beam determines the wavelength of the filter. And so that means that where the object lies on the focal plane will shift slightly. So now you will have slightly shifting interleaved comb filters. And we think this has a lot of benefit for doing high-resolution photometric redshifts. And we're also looking at how we integrate this into infrared observations like WFIRST and Euclid. And just for those of you who are disappointed that I didn't talk about asteroids, this just shows you a figure of the latest results we're getting out of our asteroid detection algorithm. These are individual postage stamps for an asteroid, and this is a coad of that asteroid with its light curve, which was found blindly, where each of these individual observations has a signal to noise of about between 3 and 5. Okay, and I'll stop there. Thank you.